Hi, I'm Julie Choi, the Chief Marketing Officer at Cerebras Systems. We're so excited to be here in Vancouver for NeurIPS 2024, and we have so much exciting research to share. Let's take a look.
Hello everyone, I'm Natalia Vasileva. I'm field CTO at Cerebras, and I oversee all of our ML projects with our customers at Cerebras. Really excited to be here at NeurIPS, and this year our team brought a lot of interesting work to share with the show. Please come see us. We see a lot of posters, a lot of excitement, ready to share additional details about all of that work the team's doing.
I'm Joel Hessness. I'm the team lead in our core machine learning team. Our team focuses on large-scale training of deep learning workloads on Cerebras hardware. The kinds of applications that we focus on most are things like large language models and things like multimodal or vision language models. Our team also has a responsibility to try to find unique opportunities for performance on our hardware. So some of the things that we study are things like training dynamics and compute efficiency for these large applications. We have a paper here that's on sparse maximal update parameterization. I'm sure you'll chat with Nolan about that. The training dynamics work that we've been doing is sort of where this comes from, that if you want to get good compute efficient training of very large applications, and if you want to do it in a way that you're not spending a lot of extra compute to make sure it's configured well, you have to manage training dynamics from the ground up. It's sort of piece by piece, each part needs to be in the right place. So we have a paper here at the conference that focuses on that. We've been extending those techniques, the maximal update parameterization techniques in general, we've extended for various different workloads and applications. And we're helping our customers do that. We actually have previously partnered with Eleuther AI and putting out some notes about how to train models in this way. So hopefully the community is able to pick those up and use them. And we've just started a collaboration with a research group that works on maximal update parameterization, like full parameterization of large language models. So we're excited that we're getting into the last bits, the final details for getting everything right here. So yeah, it's an exciting time. The reason we want to do training dynamics work is to scale up to very large models. And so the big announcement was with Sandia Labs over the last month or so. We just demonstrated that we could train a 1 trillion parameter model on our hardware. We can actually do that with a single one of our wafers. I don't know why somebody would want to train that way because it would be slow, but we have the capability to train on a single wafer. Now, if you wanted to try to do something like that on competitor hardware, you'd need a whole lot of different devices and it would take a ton of memory. Our solution is just much simpler for that. So this was an exciting demo that we partnered with Sandia to post. The cool thing was, in those first few training steps that we demoed with them, the training dynamics looked great. So we're looking forward to next steps with them where we're actually going to train one of these models.
Hi, my name is Daria, and I'm doing research here at Cerebras. I'm working on a mixture of experts, trying to train the foundational models that are compute efficient with different experts. I'm trying to train mixture of experts at a compute efficient frontier, which is a very hard problem. As you see here on my poster, there are different metrics that we developed to basically deeply analyze the architecture of mixture of experts. You can see that here are different routing methods that are state-of-the-art right now, and they have a lot of inefficiencies in terms of the expert utilization, which measures basically how many effective experts you have in the network at different layers, and also representation collapse, which is the metric that helps us understand how separate are different experts, whether they are specialized in something or they're like generalist experts like this one in particular, which doesn't actually learn how to separate the domains. So based on these metrics, the state-of-the-art methods have a lot of inefficiencies, and in our work, we are addressing those inefficiencies with a new routing method that we're going to release an upcoming paper. Towards the left, you can see here the scaling law, the beginning of the scaling law plot for different routing methods here. So we can see that, for example, for switch routing and sync core, they have better representation compared to like the hash routing. There is a significant improvement in the quality compared to the chinchilla scaling frontier. So we're beating chinchilla scaling frontier by like 4%. And you can calculate the approximate flop reduction. So you can either train to the same loss and reduce your flops by like say 5x, or you can train to the same number of flops and improve your quality by 4%. We can see that the routing really matters because for hash routing, you only gain about 1.5% compared to chinchilla, but for other methods that have a better representation, you actually learn even more. So I think mixture of experts is the next architecture that's gonna beat chinchilla, and we are training that at scale. So we started demonstrating that we can do 1 trillion model in our wafer, and I'm creating the recipe towards actually training that model to convergence at that scale.
Hi, I'm Shane. I'm a principal research scientist at Cerebras, and I work on designing algorithms that will run on our hardware and make AI training work better. Well, I mean, AI training requires a lot of computation, a lot of data to work. And what we want to do is with less computation, less power, less energy, less compute, achieve the same kind of accuracy, or scale up to larger models and get even higher accuracy. Our work is trying to make like things work better on our hardware, but also sort of advance the field of machine learning and AI in general. So we were inspired to, first of all, for one paper, to make sparse training work better. So that's like in the human brain, you have all these synapses and neurons, but not all of them are active every time you're thinking or every time you're learning things, right? But the standard kind of GPU approach to training, all of those connections are active for every input. So Cerebras allows, our hardware allows sparse training, where some of the weights, some of the connections in the neural network are zero or not being used. And we were inspired to try and make that kind of training work better. Yeah, so if I had to explain my work to a non-technical person, I would use the analogy of the brain too. Like people are kind of familiar with ChatGPT and other kinds of AI algorithms. You can think of them all running on like a brain that has all these connections and synapses and neurons inside of it. And I really want to make that brain be able to learn faster and be able to perform tasks better. And really that's about kind of designing algorithms that work really well with our hardware and with our compute infrastructure. Yeah, I think like in the field of AI right now, we know what we need to do. We need to scale up, we need to get bigger models, we need to get better models. But how to do that is a challenge. And I think that's our research really helps address this by coming up with recipes and techniques that let us try something at a smaller scale and then knowing that it will work when we do try it at a much larger scale. So it's really like the different papers we have here are about finding those really effective recipes and getting metrics that really help us scale more effectively. You know, Cerebras is a really exciting company to be part of right now. I think one thing that's different about us compared to other companies is that we're working on both training models and on the inference side. And both of those things are really exciting. For one thing, on the inference side, the more compute, the more kind of thinking you can do when you're actually generating a response, the better it's going to be. And the faster you can do that, you make things practical that weren't practical before. And on the training side, it's really exciting to think that we have hardware that can take advantage of, like I said, sparsity and kind of new ways of doing things compared to the standard approaches that are being done with GPUs. Thank you so much for joining Cerebras at NeurIPS. Check out our website and reach out if you have any questions.
I'm Gavia Gray. I work as a member of the technical staff in the ML core group. We focus on like pre-training, large language models, that kind of thing. I'm presenting a pretty technical paper. It was solving like a very specific problem that we had when we're training deep models. Specifically, you want to choose what batch size to use, but you can't test it on smaller models. You have to use it on, you have to test at large scale typically, and that'd be really expensive. So we developed a way to do that based on some prior work at OpenAI, but adapting it to work on our hardware better than on a massive GPU server farm. At a very high level, it's a way to look at the gradients, which are just like the signals that you use to update your neural network. You're trying to figure out where the signal and the noise are in those gradients and figure out how much of it is noise and how much of it is signal. And that tells you how big you want your batch size to be, because as you make your batch size bigger, you can average more of those gradients, and that gives you like more signal. I think it's a really important problem for pre-training efficiency. So you need to know what batch size to use. But in a more kind of general way, it's a really useful metric. And up until now, it was very difficult to measure it. And the only time you could ever measure it was when you were running a massive training run on like hundreds of GPUs. Whereas we've made it now so you can run it on your laptop, or you can run it on a CS2 or anything like. So yeah, I think it's exciting. We're kind of focused and excited on the same thing a lot of people are at the moment, which is just like eliminating hyperparameter tuning. I think there's a lot of stuff we do in deep learning which depends on doing these big hyperparameter tuning runs, which are really expensive. And you don't do that in like other optimization works. Like in like traditional gradient-based optimization, that's basically solved. You just set the computer running and it does it. And we need to be able to do that with deep learning. It's kind of ridiculous how we just sort of we use grad student descent. We can't do that anymore.
My name is Nolan Day. I'm a research scientist at Cerebras Systems. At NeurIPS, I'm presenting a conference paper called The Sparse Maximal Update Parameterization, a holistic approach to sparse training dynamics. The Cerebras wafer scale engine is able to accelerate sparse matrix multiplications, which means we have a vested interest in supporting sparse pre-training. So we want to find scenarios where sparse pre-training can outperform dense pre-training, which is the incumbent method. So that means we need to conduct robust sparsity studies where sparsity is given its best chance. But in our work, we found that as you sparsify networks, the optimal hyperparameters, they're not stable. They actually shift systematically with sparsity. So our method fixes this shift so that no matter what sparsity level you choose, the hyperparameters remain optimal. And this allows us to get much better losses for any sparse network. This work is impactful because there's been decades of research on sparse networks, and many of the popular papers, they've used the dense hyperparameters to train their sparse networks. But in our work, we show that that is actually very suboptimal and is artificially making all the sparse models worse than they should be. So this is exciting because it means that we can re-examine many of the past findings of papers and potentially find more exciting conclusions than what they were able to publish. And it also opens new doors for applying a similar technique, extending the maximal update parameterization to more types of sparse training algorithms. It's a really exciting time for Cerebras right now. We launched our Inference product, and it's 16 times faster than the fastest GPU solutions. And also on pre-training, we have a very exciting offering. We have a lot of traction. And so I think we have a good shot at challenging NVIDIA, both in pre-training and at inference.
Hey everyone, I'm here at the Cerebras booth at the NeurIPS 2024 conference, and I'm pretty excited because we've just announced the release of Llama 3.3. This is a model that came out last Friday, and within a matter of days, we were able to run it on our Inference service. Very exciting because we're able to get 405B level accuracy and performance using a 70 billion parameter model. Cerebras has also recently released a new framework called CPO. This is Cerebras Planning and Optimization. This is an inference time optimization that's applied using purely prompt engineering. We're very excited because once you apply this to Llama 3.3, not only can we get a highly intelligent model that's running at 2,200 plus tokens per second, but you're getting the intelligence of a 405B model with a smaller package, a smaller parameter footprint. It's been super exciting to see the reception from the researchers here at NeurIPS. We just shared this information, as I said, a little bit earlier, and people are really excited to try out the API and get their hands on Llama 3.3 on Cerebras Inference. Thank you all so much. Please reach out if you have any questions.